Hi, so this talk is about the shortest Euclidean shortest path in the plane. So we start with the problem definition. So we are given a set P of disjoint polygonal obstacles in the plane. So N is the total number of all vertices. So here the yellow are the vertices, and we have 3 obstacles. So the free space is the space outside all obstacles. So given 2 points S and T, so we want to find the shortest path in the free space. So you cannot go inside the obstacle. So if both S and T are given in the input, then this is a single shortest path problem. If S is given as a source point, T is a query point, and this is a single source shortest path problem. And we want to build a data structure to answer shortest path queries for any given query point T. So usually the data structure we use is called a shortest path map. This takes order n space and log n query time. So here is an example of shortest path map. This is S, those are the obstacles. So the red curves are bisectors. So the blue curves are also special bisectors. They are extension of from this vertex to this vertex, you get this curve extension. Given point T, we first find the cell contains T, and each cell has a predecessor, and follow the predecessor all the way back to S, then you can find the shortest path from S to T. Okay, so the lower bound of the problem is n log n. So there are in general 2 methods. The first one is you first compute a visibility graph like this, and then find the shortest path in the graph. And this algorithm takes n squared time in the worst case because the graph has n squared edges in the worst case. So the first subquadratic time was given by Mitchell using the continuous structure algorithm. The running time is n to the 3/2 plus epsilon. So, and Herzog and Suri give an n log n time algorithm. And this time matched the lower bound. But the space is n log n. So recently I reduced the space to order n in this year's SODA, and the running time is still n log n. And therefore this problem has an optimal algorithm, both optimal in time and space. But the visibility graph can only compute a single shortest path. So a continuous structure usually can build a shortest path map for all these 3 results. Shortest path map is built. Although we have optimal algorithm, but if you look at the problem and using another parameter h, which is the total number of obstacles. In this example, we have h equal to 3. In the worst case, h could be big theta of n. But in this example, you see that h is equal to 3 while n is equal to 19. So h is significantly smaller than n. Therefore, the question is, so we can have a lower bound like this, n plus h and log h time. So therefore, the open problem is, can we have an algorithm that is linear in A and with another function of h? So in particular, the problem 21 of the open problem project asks for n plus h log h time algorithm for this problem. So there are some results like n plus fh, like this one, n plus h square log n, and n plus h square and n plus h log n. So those results can compute a single shortest path, not shortest path map. So here is our result. So we get n plus h log h time, and the linear space match the lower bound, and this compute a shortest path map. But we have assumptions, so based on suppose a triangulation of the algorithm is given. So right now, the best triangulation algorithm time takes this much time. There is a additional plus epsilon there. So of course, triangulation is a different problem. But with the triangulation algorithm, so the total time is dominated by the triangulation algorithm. So hopefully, so the triangulation can be this epsilon can be reduced later. And the total time will be n plus h log h. Okay. So the main idea is we still follow Herzberg and Surrey's algorithm, and namely we use continuous structure. And then, so Herzberg and Surrey's algorithm relies on a conforming subdivision. So here we also use the subdivision, but use a smaller one. And then we use the same technique to reduce the space to linear. Okay. So first, we're going to quickly review the Herzberg and Surrey's algorithm, and we call the algorithm an HS algorithm. Okay, again, the algorithm uses a continuous structure approach. The difficulty is how to maintain the wave front, which consists of all points with the same distance from S. So here I have, let me show you animation of continuous structure. So, okay, so this is the video from sausage 14. So the green point is the source, and the white are the free space, the black are the obstacle. The red curves are the bisector. They are not from the input. So this is something we need to compute in the algorithm. The green path is the shortest path. So if I start to generate a wave front, it's like this. That's the wave front. So eventually the wave front will cover the entire space. So you see the difficulty is how do you know what is the next vertex hit by, for example, this here, this the first vertex hit by the wavefront. So how do we find that vertex? So this is the event point. So that's a difficulty. For example, in Mitchell's algorithm, he reduced the problem to a semi-algebraic range query problem in high dimensional space. So I think each query is answered in n to the 1/2 plus epsilon. That's why the total time becomes n to the 3/2 plus epsilon. And also you see that at this moment, these two parts of wavefront will collide with each other. So how do you detect those clearly, right? So like here it will collide. How do you do? So that's the difficulty of the using continuous structure. Okay, go back to. So here, a wavefront is basically a sequence of so-called wavelet. So, so in this example, and this dashed curve is a wavefront, and this red piece is a wavelet. It is a part of a circular arc centered at the obstacle vertex, like this red one, and this vertex is called a generator. So for any point in this wavelet, the shortest path from S to the green point must contain this red point. And the wavefront is represented by a list of generators. So a wavefront is a sequence of wavelet, and we use the generators of those sequence of wavelet to represent a wavefront. So in this wavefront, we have those red points are the generators. So for example, this piece of wavefront generator, this one, this piece of generator, wavefront generator, this one. So basically, to implement the wavefront expansion, we need a geometric data structure to guide that. So because of that, the Herzberg and Surrey propose a so-called conforming subdivision of the free space. So this is the picture I copied from their paper, and you see these are the two obstacles. So the subdivision has order n cells, and each cell has a constant number of edges. And there are two types of edges, so-called transparent edges, which are the edges in the free space, and opaque edge, which are edge on an obstacle. And each transparent edge, like this edge E, has a well-covering region in this gray area. And this region has order n cells, and E is inside this region. So an important property is called a well-covering property. So namely, for any edge on the boundary of this region, and between any point of F and any point E, the distance is larger than 2 times the length of E and 2 times the length of F. So that's a very useful, very important property. So, and the subdivision can be constructed in log n time in linear space. So, and we use this subdivision to guide the wavefront expansion, but the difficulty is, again, is maintaining a true wavefront is very difficult. So instead, the algorithm maintains two one-sided wavefront WE for each edge S of E of S, each transparent edge. So like this edge, so this is a wavefront. We have three generators, and the wavefront is going upwards. So that's one-sided wavefront. And you have another side wavefront going downwards. So each wavefront represent the wavefront coming from one side of E. And then you starting from the source point S, we propagate the wavefront cell by cell in S. So, and during the propagation, we need to process the so-called bisector events. So there are two types of bisector events. The first type is here we have 3 generators and we have 2 bisectors, and the 2 bisectors intersect at P. So before P we have 3 generators, but beyond P, the middle generator will be removed. So this is a bisector event. Another type bisector event here, the bisector intersect obstacle, the intersection point is a bisector event. So therefore we need to process those events. So the total time space, so there are order n bisector events in that entire algorithm. So each wavefront is represented by a persistent binary tree with path copying. So we have to do that. So each event costs log n time and log n extra space. And therefore the total time and space is both n log n. So then again, the space can be reduced to order n. So basically you follow the same algorithm, but you partition the algorithm into log n phases. And in each phase, you still need, we still use the persistent tree, but each phase costs order n space. And at the end of each phase, you do a space reset operation. And so that you store a so-called snapshot, which takes order n space, then can guarantee the algorithm can proceed as usual. And then the space, the total space is still order n. So I'll omit the details for that part. So next, we talk about how to reduce the time to n plus h log h, which is the new result of our paper. So we first reduced the problem to the convex case. So namely, all the obstacles are convex. So this is used by a corridor structure. This is a traditional technique, but there is a key sub problem we need to solve. So let's first focus on this convex case. So here you see that this is the shortest path. So again, we need to generalize the HS algorithm. And suppose we have H convex obstacles and N as the total number of vertices. So we introduce a new notation, set P as the set of rectilinear extreme vertices of all obstacles. So namely, those are leftmost, rightmost, topmost, bottommost vertices. So each obstacle has 4, and therefore V, the total size of V is at most 4H. And then we compute a conforming subdivision SV of V, and this takes H log H time, and the size is order H, because the size of V is H. And the vertices of V also divide each obstacle boundary into at most 4 convex chains. Actually, each like this is a convex chain. Actually, this is both X and Y monotone. So in total, we have order H convex chains. So that our algorithm will treat each convex chain as a single unit, although it's not a constant size, but it's still conceptually we consider that as a unit. So we have order H unit instead of order n vertices. So and then next we're going to insert those convex chains into SV to obtain a conforming subdivision SF of the free space. So here the total time is n plus h log h instead of n log n as in the original algorithm. So again, here is the free space, the conforming subdivision in the original algorithm. So here is the subdivision in our algorithm. You see the difference. So like these cells, each cell, this cell may not be constant size because this part of boundary is from an obstacle. It may contain many vertices. And therefore the cell size, each cell may not be constant size, but it has the boundary of a cell has at most order and convex chains, which means it has a constant number of units. And we use this subdivision to guide our wavefront expansion. So also, so now a generator is not a single vertex, it's a convex chain. So like this one, so this is a wavelet. And in this wavelet, for each point, like this one, the shortest path is you connect this one to the green point until S. And therefore the wavelet, you see that this wavelet now has 3 pieces. It's not a constant size. It may have many pieces. It is depending on the size of this convex chain, namely the generator. But once given S and this convex chain, we can determine this wavelet implicitly. And also because the generators are convex chains, the bisectors, the bisector of 2 generator may not be constant size as well. So like this one, I have those two are 2 convex chains. This one is the bisector. It has 1, 2, 3, 4, 5 pieces. So each piece is constant size, but the total bisector may not be of constant size. Okay. So because the bisector is not constant size anymore, so some operations of bisectors may not be solved in constant time as before. So for example, if you have 2 bisectors, you want to compute the intersection. In the original HS algorithm, each bisector is constant size, so this is a constant time operation, but now it's not. And also, if you want to compute the intersection between a bisector and an obstacle, like this one, again, it's not a constant time. So, but what we do is we use the tentative point search technique, and we can perform each operation in log n time. So next, we briefly talk about how we propagate the wavefront in an individual cell of the conforming subdivision. So now we consider, so this yellow one is an empty cell, namely it does not intersect any obstacle. So suppose we have a wavefront from the bottom side going upwards. So A, B, C are for example, A, B, C are the generators. So the blue curves are bisectors. So what we need to do is propagate this wavefront to compute the wavefront on the left and the top and the right, the other 3 sides. So what we do is we're going to sweep a line from the bottom all the way to the top. And we're going to process all the bisector events. So here the bisector events are simply because there are no obstacles, and the bisector events are the intersections of bisectors inside this rectangle. For example, and this is the lowest bisector event. This one is lower, but it's outside, so we ignore that. So this event is determined by these 3 bisector ABC. To process this event, what we do is we simply remove B from the bisector list, and now we recompute the bisector of A and C. So this dashed one is the bisector A and C. And eventually, after we process all the events, we have a situation like this. And these three are the wavefront for the left side, and those are the wavefront on the top side. And these two are the wavefront on the right side. So this is the case for a cell that does not intersect any obstacles. If a cell, for example, the left or right side of cell is a convex chain on the boundary of obstacle, and the situation becomes more complicated. So in this case, a new generator can be created at the tangent point. So for example, this is the common tangent between this convex chain and this generator. And this is the common tangent point Q. And there will be, so this is the bisector between this generator and this generator. And this bisector does not intersect this convex chain. So in this case, a new generator will be created at Q prime. So let's look at an example. So this is a cell at the left side is a convex chain, which is a part of an obstacle. So in this case, again, we will have bisector events as bisector intersections. And also, in this case, we have an intersection between the a bisector and the convex chain, which is an obstacle. So therefore, we look at the leftmost bisector, and this is the lowest bisector intersection. But this intersection is lower than this one. Therefore, we process this this event first. To do that, we simply remove A from the bisector list. In another case, if the leftmost bisector does not intersect the convex chain, and for this case, we're going to compute a common tangent between A and the convex chain, which we have a common tangent point P. And now P is below Q, therefore we process P first. To process P, we simply create a new generator at P. And then next we're going to process Q in the same way as before. So to bound the running time by n plus h log h, we have to use a global charging scheme. I mean, in the original HS algorithm, this is done, and the time analysis is done locally for each local operation, log and time. But here we have to consider the entire algorithm in a global way. So the analysis is more complicated. Finally, just a few slides explain how to reduce the general case to the convex case. We only talk about a special case, actually, if all the convex cause of all obstacles are disjoint. If they do not disjoint, then we can use a corridor structure to the algorithm is similar. Again, our the main focus is on a main sub problem. So again, so in this case, if T is outside the convex halls, then the shortest path from S to T is also outside the convex hall. Therefore, what we do is we compute the shortest path map from S in outside all convex halls. So this is the convex case. So we apply our convex case algorithm. And next, you see that there are some pocket, like this one is a pocket. So the pocket between the convex hall and the obstacles. So what we do is we're going to extend the shortest path map inside those pocket through their gates, like those green edges, the gate. This is the gate. This is the gate. So this is a key solve problem. I see here is a better picture. So we have a pocket here. The gate is from C and D, and those obstacles are outside. So suppose we have a shortest path map outside the pocket. So those red curves, and including these two, are bisectors. And those vertices on CD are the intersections of bisectors with CD. So the subproblem is we want to extend the map inside the pocket. So here we have M as the number of vertices on CD, and the capital N is the number of vertices of the pocket, and the capital G as the number of vertices on the generator. So those black edges are generators. So each of them is a convex chain. Suppose G is the total number of vertices on all these generators. So we present an algorithm n log n, m log m plus n and plus G time. So this algorithm may be interesting in its own right, I guess. So over all pockets, so the sum of m is order h, the sum of n is order n, and the sum of g is order n as well. And the total complexity for all subproblems for all pocket is m plus h log h time and order n space. So after that, after you extend the map into all pocket, then we obtain shortest map in the entire free space. So this finished everything, I think. So thank you for your attention.